In this video, we will look at a problem involving projectiles. We will do it 3 different ways, and hopefully you will see how writing things in vector and non-vector form are different mathematical ways of writing the same bit of science. Here's an object on a cliff. We launch it from the cliff at 20 meters per second, 36.9 degrees above the horizontal. It is subject to Earth's gravity, but assuming zero drag there are no other forces, so the acceleration is always g downwards. It follows a parabolic path like this. The question is, if it lands at the bottom of the cliff 5 seconds later, with what speed does it hit the ground? We can resolve the initial velocity vector into horizontal and vertical components, and they turn out to be 16 and 12 meters per second respectively. That's why we chose the weird angle 36.9 degrees, in order to make these components come out as nice numbers. We can use uniform acceleration formulae in the vertical direction. So here, the final velocity Vy is equal to the initial velocity Uy plus the extra velocity gained through acceleration. Substituting values for Uy, A and T gives an answer of minus 38 meters per second, or 38 meters per second downwards. And horizontally there's no acceleration, so V in the x direction is the same as U in the x direction, which is 16 meters per second. Then we can recombine the velocity components using Pythagoras to give a final speed of 41.2 meters per second. Here is exactly the same question again, but we are going to express the initial velocity components in terms of the unit vectors I and j. Because the acceleration is a velocity and acts downwards, it too is just a multiple of j. Here is the initial velocity expressed in vector form, and using the vector version of the same uniform acceleration formula we used before gives this, where the green part is the initial velocity and the red part is the extra velocity due to the acceleration. Performing the calculation gives a final velocity vector of 16i minus 38j, which leads to exactly the same drawing and exactly the same calculation of speed as we did before. And our final way of expressing this problem is to use the vector version of the equation again, but expressing the vectors in column form. Notice how the acceleration is expressed in this form. This column vector represents minus 10j. Here's the initial velocity expressed as a column vector. To perform the calculation we work across the top row and then across the bottom row, so that horizontally we have 16 plus no change, and vertically we have 12 minus 50. Again, it leads to the same vector diagram for the final velocity and the same calculation for speed. All 3 versions are equivalent in terms of the physics going on. They are just 3 different ways of notating the maths describing the physics.